Hello. I'd like to give a very short introduction of PageRank today. Basically, PageRank is the earliest algorithm employed by Google to sort out the importance of different web pages. And the basic idea is very simple. I guess a little bit background for the authors. Of course, they are the inventors of Google. Inventor of the algorithms and the founders of the Google. And also both of them have parents actually work in academia. Therefore, they are actually quite familiar with the how the citations in academia work. So the PageRank algorithm is more or less taking aboard the idea of importance in academia in the sense that if a page is linked by many other pages, in the sense that like it has lots of backlinks, then it's likely to be important. It's kind of reasonable. But also, like, we need to consider that even if a page doesn't have lots of backlink, but if one of its backlink is actually very important, then there's a good chance that that page will be important as well. So we have to take into account this kind of cases. PageRank is a very intuitive algorithm, really. What's going on is we can interpret it as, let's say, we have, for example, here have just 3 pages, and let's say I have a reader that is reading page A for the moment. So whenever we have a link, we can just imagine that in the next minute, there's a chance that the reader will just switch to the other pages that link by this page. So for example, in the next minute, the reader will either switch to page C or page B. And like for this reader C here, there's a probability that in the next minute it will switch to page B, or like it will stay in page C, and so on. And of course, one of the first issue is like we don't know the probability exactly. So therefore, like a very reasonable assumption will be just assume that like the probabilities, the outgoing probability are all equally distributed. So therefore, like for example, for page A, there's 50% chance to point to the reader will move on to page C, and 50% chance to move on to page B. And for page B, there's since it only have one link linking to page C, we'll just assume that it will for sure will switch to page C. And for page C, it will have 50% chance that the reader move on to page B, and there's 50% chance that it will just stay on page C. Now let us imagine that at the beginning there's a large number of readers. Let's say just 1 million of them. Let's say just 1 million for readers, and let's say just like there's 200,000 that is reading page A, and like 300,000 is reading page B, and let's say 500,000 is reading page C. Now, how many reader will there be like in the next minute, like for each of the pages? It will be very simple. Right? We can write down like a matrix. Of course, we can just compute like for example, for page A, let's say just look at page B first. For page B, the number of reader, let's say I just call it B is something like reader B XB 1 in the next minute will be just equal to the number of reader. Let me see. That will be either readers from page A, that will be like 0.5 of the readers from page A, that let me, instead of like this 200,000, let me write it as XA0, for example, representing at 0 initial period of time and number of people in A, and this xb0 and xc0 and so on. So I have this is basically number of people for B will be 0.5 xa0 plus, if it's B, it's not going back to itself, therefore it's just 0 xb0 plus C will be it'll point to them. So what 0.5 to point to, if it's in xc, there's 0.5 to point to B, so xc0, and I can do the rest, something like xc1 is equal to xa1. Actually, no one is pointing to it. It's basically 0 xa0 plus 0 xb0 plus 0 xc0, and C will be let's see, 0.5 xa0, that's from A, and from B will be 1 xb0 plus C will be 0.5 xc0. And I can write this in a matrix equation. I just call this as a vector as A, x1, let's say x1 is xa1, xb1, and xc1. X0 is just xa0, xb0, and xc0. Then I can see that x1 is just equal to 0, 0, 0, 0.5, 0, 0.5, 0.5, 1, 0.5, and x0. Maybe I can call this matrix M here. And so apparently, if I want to look at, like, after a long period of time, how many people will be reading in each of these pages, I can just like keep on multiplying this M by the current number of people reading each of the pages. So I can have x100, for example, would be like M to the power 100 times x0 and so on. And eventually it will just converge. And also, instead of like x as the number of people, maybe I can think of it as the fraction of people. So therefore, maybe I can use y instead. It's like the number of the fraction of people reading each of the pages, and that will be like initially it will be like 0.2, 0.3, and 0.5. So then, actually, what PageRank is trying to capture is like just after a long period of time, how many people will be reading, or like the fraction of people will be reading each of the page. But as you see, there's one problem here that is not very realistic. It looks like that, like, just after one transition, there will be no one reading page A. That probably is not correct. So instead, like, one modification of this algorithm can be, let's say, for the transition, there's a chance that either it will move on to other pages, but also there's a chance that it will just stay, like I shouldn't say, there's a chance that it will move on to other pages there, but there's some chance that, like, it will start from a new page. Basically, a reader just start from scratch again, and then maybe he will start like reading page A again. So then let's say the probability that it will move on to a new page will be theta. Let's say, for example, let's say theta is 0.8 here, that move on to a new page. And so therefore, like, I can write, for example, x1 is theta times m x0 here, and there's also 1 minus theta that it will start from a new page. So plus 1 minus theta, let's say just v here. V is just the kind of like approximate probability that we imagine, like, what's the probability that a reader will start looking at each of the page, like if they start a new page. So of course there's a problem here is that we don't know what's V here. Another very reasonable assumption, let's just assume V is uniformly distributed again. So let's say V is just equal to, in this case, 1/3, 1, 1, 1, something like that. And this we can know that since x here, x0 is a probability, if you assume x0 is a probability, it will sum up to 1. So therefore, x0 times 1, or like this is 1 transpose times x0 will be just equal to 1. It's a scalar 1 here. This 1 transpose here is 1, 1, 1 here. And x0, for example, originally we said like x0, oh I'm sorry, I'm using y0 as the probability and x0 as the number of people. Let's change it to y1 and y0. In this case here, I like to use the fraction here. So up to this stage, I like to use the fraction. So y0 should sum up to 1. So y0 initially is this 0.2, 0.3, 0.5. So apparently, because they sum up to 1, 1 transpose times 1, 0 is just equal to 1, a scalar 1 here. So therefore, like, it's okay for me to also plug in this y 1 transpose times y 0 here. So, but if I do that, basically this is just a matrix times a vector is again a matrix also. So I can use the associative law that I say this is like multiplying like this. So therefore I can rewrite that as y1 is equal to theta m plus 1 minus theta v1 transpose times y0. Now this is the update matrix that we can use. Like for example, we can call this G here. This is the Google matrix, let's say. And again, like as what we did previously, if we just keep iterate this G for many times, we'll eventually find like the fraction of people reading each of the pages, like as it converges over a long period of time. That's, imagine that after a long period of time, what fraction of people reading each of the page. Actually, for our example here, if we don't have this adjustment, the original approximation will be like 0, 1/3 and 2/3. And like after this adjustment here, y, let's say infinity, is something like 0.66, I think it's 0.67, something like this is 0.6, this is 0.333, something like this. For one last thing, I just want to say that we can of course iterate this for many times, but another interpretation is if we think of this G here, G times y is equal to y in general. If we have look at like what is the at iteration n, yn plus 1 is equal to gyn. So if n is very big, that is approximately converge, then yn plus 1 is just equal to yn, or like at least approximately equal to yn. So therefore, like g minus I is equal times yn is equal to 0. So as we can see here, this yn, then actually this thing, if you you're familiar with linear algebra, then you realize that this is very similar to computing the eigenvectors and eigenvalues of a matrix. Actually, if you basically have for eigenvectors or like eigenvalues that is of an M matrix, will be just referring to vectors that mv is equal to lambda v. Basically, when you multiply by a vector v by the matrix M, it's not going to change the direction of v, and that is the eigenvector, and corresponding lambda is the eigenvalues, and we immediately see that m minus lambda I v should be equal to 0. And if we compare these two equations here, we can see that yn is basically just the eigenvectors for the matrix G, and with the eigenvalues lambda is equal to 1. I'm not very articulate here. Maybe I just write it here. Maybe yn is eigenvector of G with eigenvalue 1. Okay, that's my conclude my kind of very short introduction of PageRank, and thank you for your